So digging into a little bit more about the principal quantum number, the first thing to talk about is what are acceptable values for the principal quantum number. And this one's pretty easy. N is going to equal 1 or 2 or 3 or 4 or 5, on and on as we go up. And as we get into larger and larger energy shells, we're going to be able to fit more electrons in it. So in the first one, you can fit 2 electrons. In the second one, you can fit 8 electrons. In the third one, you can fit 18 electrons, 4, 32, 5, 50, 6, 72 electrons. And as we go higher and higher, we're going to see that each one of these shells has a higher and higher energy associated with it. Now, it would be really convenient to think that like we fill the first shell and then we fill and then we start filling the second shell, and then after that's full, we fill the third shell. And at first, for the first 20 elements, that's actually true. We first fill the first one, and then we go ahead and fill the second one, and then we start filling the third one. But after that, when we get to higher energy shells, we start kind of skipping around back and forth, actually, before and when we're filling them in. So things start to get a little complicated when we get to these higher energy shells. There's a rule for how many electrons can fit in an energy shell. That's where I'm getting these numbers from. And the rule is that the electron capacity for any one shell is going to be equal to 2 times n, the shell number, squared. So for instance, for shell number 4, we have n equals 4. We have 2 times 4 squared. 4 squared is 4 times 4, or 16. We have 2 times 16. 2 times 16 is 32. And we can fit 32 electrons in there. A couple of takeaways from this. The higher the principal quantum number, the higher the energy of the electron. When we have higher energy electrons, it may be found further from the nucleus. It's not a guarantee that it always will be, but it's allowed to go further from the nucleus. And these higher energy electrons will be the first ones lost during chemical reactions. And we're going to be getting into, soon in the next couple of weeks, reactions where we're going to talk about electrons leaving one atom and going to another. So the next quantum number I want to talk about is the angular momentum quantum number. This is L. And every value that L takes on is going to have a letter corresponded to it and a shape of an orbital that corresponds to it. So acceptable values for L depend on which energy level you're in, and it's going to vary from 0 up to n minus 1. So when n is equal to 1, the only quantum number we can have, or angular momentum number we can have, is 0. This corresponds to the letter S. We might say an s orbital. And an s orbital is going to have the shape of a sphere. The next value we can take on is going to be 1. This corresponds to a p orbital. And the p orbital has this kind of three-dimensional dumbbell shape, where we have kind of a spherical sort of little guy down here and a spherical guy up here, and then this little, what they call a node in between. The next angular momentum number would be 2. This corresponds to d orbitals, and this is where things start to get a little complicated. One shape that a d orbital can take on looks kind of like this, where we now have this like clover type shape around the center. But in fact, not all d orbitals are going to look like this. there are some really exotic shapes that it can take on. I'm going to upload a document where you can take a look at some of those shapes, but it's not really going to come up in our homework, so I wouldn't worry about it too much. In the third angular quantum number, we get the f orbitals, and these start to take on pretty complicated shapes, like this 6-lobed one. And again, not every f orbital is going to look like this. There's a lot of different shapes that it can start to take on. If we take a look at this table, we can see which sort of L values are permissible in each one of our shells. So when n equals 1, we can only have L values of 0, right? Because it's going to be between 0 and n minus 1 is 0, so it only can be 0. And in that energy shell, we can only have s orbitals. When n equals 2, L can be 0 or 1, and we can have s and p orbitals. 3, we get 0, 1, and 2. We can do s, p, and d orbitals. And in 4, we get 0, 1, 2, and 3. We get s, p, d, and f orbitals. There are higher n values, and in theory, those would open us up to higher L values. But in fact, we've never actually observed that. We've only ever observed S, P, D, and F orbitals. So there's a possibility that in fact this all breaks down and there are no other orbital types. Okay, so let's talk a bit about the magnetic quantum number. So m sub L is going to take on values between negative L and positive L. So let's think about the first case where we have L equals 0. So when L is equal to 0, ML is also going to equal 0. And this is going to lead us to only having one kind of s orbital. So we just have this s orbital right here that's a sphere. And I'm going to come back to this in just a moment after we talk about the p orbitals. So for p orbitals, or L equals 1, our permissible values for ML are going to be negative 1, 0, and 1. And the orbitals that are going to be possible are the px orbital, the py orbital, and the pz orbital. And this is how those are going to work out. So if I laid out a grid here with y, x, and a z axis, right? So that's the same as my pencil, say being like x, y, and z coming out of the page. Then the px orbital is going to be arranged along the x-axis. The py orbital would be around the y-axis, and the pz orbital would be aligned along the z orbital. So that leads to 3 different kinds of orbitals. And if we think back to the example where we just had the one s orbital, that kind of makes sense, because if this is a sphere, I can turn it any old way that I want, but I'm never really going to be able to see that. It's always going to be the same. So any way you turn it, it doesn't really matter, right? Think about like somebody spinning a basketball on their finger. Without seeing the surface moving, you really could see that it almost appears as if it's not moving at all. And then once again, for the d and f orbitals, things start to get a little bit more complicated. We're not just having different arrangements of the orbitals, but actually sometimes even changing the shapes of the orbitals as we go along. So the final quantum number is our magnetic spin quantum number. And the possible values for magnetic spin depend on what kind of particle we're talking about. But lucky for us, we're only really talking about one kind of particle, the electron. And for electrons, there's only two possible values. You can have an ms value of -1/2, or you could have one of 1/2. There are a lot of texts that describe spin as the actual spinning of an electron. And for some really technical reasons, that's not really a good way to think about it, and we can't really test to see if an electron's really spinning anyway. What's important to realize is that what spin is the smallest unit of magnetism, just like charge would be the smallest unit of electricity. And I think that it would probably be best that we just kind of leave it at that. So, to understand spin, it's convenient to think about magnets, right? So if I had two bar magnets and I arranged them with the positive ends next to each other here and the negative ends next to each other here, they're going to repel each other. These two are going to repel each other and these two are going to repel each other. And it will even make one of the magnets want to flip around. So this is not a good configuration. It's not stable. Similarly, it wouldn't be stable if I had both the negatives up and the positives down. I still have the same signs next to each other, and I still have a problem with stability in this case. What they do like to be in a resting position in is if I have them with the opposite signs next to each other. Okay, and if I do that, they're going to attract each other, they're going to stick together, and we get a very stable configuration. So mathematically, this arrangement would be like a situation where I had a positive 1/2 and a positive 1/2 spin in this two electrons with positive 1/2 spin in the same orbital, and that's not a stable configuration. And mathematically, this type of configuration would be the same as having two electrons in the same orbital that both have negative signs, -1/2 and -1/2. And that also is not stable. Instead, in every orbital, we want one electron with a -1/2 value and one electron with a 1/2 value. And the other thing I want to point out is what this little picture is right here. You're going to see this pop up later on if you continue in chemistry, where we're pictorially representing the spins of electrons in an orbital. So I have this horizontal line. This represents some kind of an orbital. I might label it underneath it. And I'm going to label an electron as a little arrow, one of these little half arrows, and a value of being up, pointing up, is going to correspond to a positive 1/2, and being in a down position is going to be -1/2, and just the same rules apply. So both of them being up is not a stable thing. We don't want that. Both of them being down is not a stable thing. We don't want that. We want one facing up and one facing down. A consequence of the ms values and the magnetic spin of electrons is that each orbital can hold a maximum of 2 electrons. So you can have 0 electrons in an orbital, you can have 1, you can have 2, but you don't get to have 3, and you certainly don't get to have -1. And again, 2 electrons sharing an orbital are going to have opposite spins. So they're going to have opposite signs for their spins. Okay, so let's see if we can talk about electron configurations. So an electron configurations are a type of list. And this list is going to specify the n values and the l values for each orbital that an electron is occupying in an atom. It's also going to specify the number of electrons that are in each of these types of orbitals. So I have a little list here to introduce some of the notation that we're going to be using. If I was in the first principal quantum number energy shell and I had an s orbital, I would write it as 1s. And in there, I can have a maximum of 2 electrons. Then I could go up to the 2s one. I would have a maximum of 2 electrons possible in that guy. The 2p, however, we know that there's 3 of those now. And so I would have a maximum number of 6 electrons that I could fit in a 2p orbital. If we skip ahead a little bit to 3d, we'll see that you can fit 10 electrons in it. And then skipping even further ahead to 4f, we can see that you can have 14 electrons in the 4f orbitals. Now it would be really convenient, once again, if things just filled in according to this sort of scheme, but in fact this is not how they're filled. So the order that electrons get filled in is dictated by something called the Aufbau principle. This is a German word, Aufbau. And I think it's best described by this pictorial here, where we just are going to kind of trace along this serendipitous path. So you can see that here we see that in n equals 1, we get the 1s orbitals. N equals 2, we now have opened up 2s and 2p. N equals 3, we get 3s, 3p, and 3d. But when we're filling them in, we're going to follow along this path. So first we're going to do the 1s ones, then we do the 2s ones. Everything's making sense. Oh, now we get to do 2p. That even makes sense. We do 3s. Then we're going to fill in 3p. And all of a sudden things get a little bit more complicated. And instead of going and filling in the 3d right away, we're going to go to the 4s and fill that guy in. Then we're going to come back around and we're going to finish filling out that third energy level with the 3d orbitals. And then we'll move on to the 4p's, and then we fill in the 5s's before we get to the 4d's, and so on and so forth. So now we're ready to take a look at an example problem. What is the electron configuration for oxygen? How many electrons are in its second energy level, meaning n equals 2? How many electrons are in the 5 orbital, or in the s orbitals, where L is equal to 0? So the first question we need to answer is how many electrons are there in oxygen? If I take out my periodic table and I go and look up oxygen here, I'm going to find that it has a chemical symbol that looks like this. It has a mass of 16 and an atomic number of 8. And what we're going to assume when we're talking about these problems is that there's an equal number of electrons and protons, therefore giving us a neutral atom with no charge on it. If it did have a charge, it'd be what was called ionized, and we're going to talk about ionization and ions in subsequent weeks. But for this week, we're going to assume that 8 protons means that there's also 8 electrons. And then what we're going to need to do is go to our little list here and start filling them in. So I need to fill in 8 electrons. So first I'm going to go to 1s, and I'm going to imagine I put 2 electrons in there. And I'm going to write that as 1s with a subscripted 2 to show that there are 2 electrons in that 1s shell. Next, I'll go to 2s. I put 2 electrons in there. I've now filled in 4 of the 8 electrons. And I'm going to write that up here as 2s superscripted 2 to indicate that there are 2 electrons in that 2s shell. Now, I need to fill in 8 electrons. And that means I have, and I've already done 4, so that means I have 4 electrons left to place. I know that this 2p can hold 6 electrons, so I can put all 4 of the remaining ones in here. It'll have plenty of room for it. It can still accept 2 more electrons, but I'm all done. I've filled in all my electrons. And I'm going to write that as 2p superscripted 4. Now, as a little check, I'm going to think about there are 2 electrons here, 2 electrons here, 2 electrons here, 2 plus 2 plus 4, or 4 electrons here, 2 plus 2 plus 4 is equal to 8, and I've filled in all of my electrons. Now, let's answer these other questions here. We have our electron configuration, but we asked how many electrons are in its second energy level when n equals 2. So this is a orbital in the second energy level, and this is an orbital in the second energy level. There are 2 electrons here, and there are 4 electrons here. So together, there are 6 electrons with n equal to 2. The other question is how many electrons are in the s orbitals, where L is equal to 0. Well, this is an s orbital, and this is an s orbital. They both have 2 electrons, so together there are 4 electrons where L is equal to 0. So I want to introduce for you guys a bit of alternate notation. And it's just a different style of writing electron configurations. So in this way, if we started to write out configurations for larger elements, we're going to have a really long run-on here for the electron configuration. And the beginning really isn't ever going to change. When we do reactions and stuff, that's all going to happen with the higher energy electrons over here on the right. So one way to help abbreviate this is to introduce what they call noble gas notation, where we start off with the next lightest noble gas that's a little bit smaller than the element we're looking for. We write its chemical symbol inside these brackets, and that stands in for the configuration for that gas. So for instance here, the electron configuration for helium is 1s2. If I plugged in 1s2 here, I would get back to this configuration. And that's pretty important actually, because what that's going to allow you guys to do is to use this table that I've uploaded for you guys. Let me just see if I can bring that into a little bit better focus for us. And this guy is really our secret weapon for electron configurations. Let me show you how we can interpret this. Let's say that I want to write down the electron configuration for silicone. Well, I would go back, meaning to the left, and then up to the next lightest noble gas. So here I have neon. And I would write the electron configuration for silicone as neon. And then this piece right here. 3s2, 3p2. If I wanted to expand this out some, I would go and take a look at neon here, and neon is going to be helium plus this bit. So I could write that over here. I'm going to have helium plus 2s2, 2p6. Plus this part right here. And then if I wanted to write out the full configuration, I would just have to replace helium here with 1s2. And then I have the full electron configuration for silicone. So that would be 1s2, 2s2, 2p6, 3s2, 3p2. So using this table, we'll be able to quickly write electron configurations for any element. And once you have the electron configurations, it'll be pretty trivial to be able to answer the questions that you're going to see on our homework for this week.